Somewhere in the dark, a star is dying. For 10 million years it burned, fighting gravity with fire. Now the fire is gone, and in a single silent instant, the star collapses inward, faster than thought, faster than light could cross a room, folding into a point so dense that space itself tears open around it. A black hole is born. Nothing that falls past its edge ever returns. Not light, not matter, not information. Drop a book into it, a planet, an entire library of human knowledge, and it vanishes, swallowed by a darkness so complete that even the laws of physics seem to go quiet at its border. For decades, we believed that was the end of the story, that black holes were eternal, perfectly black, perfectly silent, tombs from which nothing escapes. We were wrong, because black holes are not eternal. Slowly, impossibly, they leak. They glow. They shrink. And after an unimaginable stretch of time, they disappear completely, evaporating into nothing, as if they were never there at all. Which leaves us with a question so simple a child could ask it, and so dangerous it has haunted physics for half a century. If the black hole is gone, where did everything go? Where is the book, the planet, the information that fell inside? If the answer is gone forever, erased from existence, then one of the deepest laws in all of science is broken. And the universe, at its core, stops making sense. This is the story of the greatest paradox in modern physics: egos, and impossible ideas. A mystery that pulled our smartest minds to the very edge of reality. To ask what happens when the two rulebooks of the universe are forced, at last, to collide. To understand why a vanishing black hole terrifies physicists, you first have to understand something strange about our universe. We don't have one set of rules that explains everything. We have two, and they don't get along. The first rulebook is for the big things: planets, stars, galaxies, anything large enough to see. It was written by Albert Einstein, and we call it General Relativity. It describes gravity not as a force pulling things together, but as something far stranger: the bending of space and time itself. Picture a heavy ball resting on a stretched sheet of fabric. The ball sinks, the fabric curves, and anything rolling nearby gets pulled toward it. That curve is gravity. The sun bends the space around it, and the Earth simply follows the dip. It's beautiful, precise, and it has passed every test we've ever thrown at it. It predicted black holes. It predicted the ripples in space we now call gravitational waves. When it comes to the large-scale universe, Einstein is almost never wrong. The second rulebook governs the small things: atoms, particles, the flickering machinery hidden inside every speck of matter. We call it quantum mechanics, and it is one of the most successful theories in all of science. Every phone, every computer, every laser and medical scanner works because we understand these rules. But quantum mechanics describes a reality so bizarre it barely feels real. Down at this scale, certainty disappears. In our everyday world, a thing is here or it is there. A ball is in your hand or it isn't. But a quantum particle refuses to commit. Until you look at it, it exists in a haze of possibilities, a smear of maybe here, maybe there, everywhere at once. Only when it's measured does it snap into a single, definite location. And there's a hard limit written into nature itself on how much you can ever know. Pin down exactly where a particle is, and its speed becomes a blur. Measure its speed, and its position dissolves into fog. This isn't a flaw in our instruments, it's a rule. At the smallest scales, reality isn't solid. It's restless, fuzzy, and impossible to fully nail down. So here is our problem. We have one rulebook for the big and one for the small. Einstein's smooth, curving space-time for the cosmos, the jittery, uncertain quantum world for the tiny. And for almost everything in the universe, you only ever need one of them. A galaxy is huge, so you use gravity. An atom is minuscule, so you use quantum mechanics. The two theories rule separate kingdoms, and they almost never have to meet. Almost. Because there is one object in the universe where both rules apply at the same time. One place where something enormous is crushed down into something unimaginably small. And in that place, the two rulebooks are forced to sit at the same table. And they immediately start to scream at each other. That object is a black hole. To see why, follow what actually happens when a giant star dies. For its entire life, the star survived by balance. Gravity was constantly trying to crush it inward, and the fire in its core pushed constantly back out. As long as it kept burning, it held its shape. But no fire lasts forever. When the fuel finally runs out, the outward push vanishes in an instant, and gravity, which never rests, wins completely. The core collapses, and nothing stops it. Here on Earth, if you crush something, it eventually resists. Atoms push back. Matter holds its ground. But in the heart of a dying giant, gravity is so overwhelming that it smashes through every barrier nature has. It crushes atoms. It crushes the particles inside them. And according to Einstein's equations, the collapse continues until matter is compressed into a singularity, a point where the mathematics itself ceases to make physical sense. Because when Einstein's equations are aimed at that point, they don't give an answer. They give infinity. And in physics, when your theory outputs infinity, that's not a discovery. It's a warning. It means the theory has hit the exact edge of what it can explain and fallen off the cliff. General relativity, the rulebook that has never failed, simply breaks. And here's the crucial part. Whatever that point is, it's no longer in Einstein's kingdom. The collapse has compressed everything down past the atom, past the particle, into a realm so small that the fuzzy, uncertain rules of the quantum world must take over. So we do the obvious thing. We reach for the other rulebook. We try to describe the singularity using quantum mechanics instead. And that fails too. Because quantum mechanics was never built to handle gravity. In the quantum world, particles live and interact against a fixed, calm background of space and time. A stage that stays perfectly still while the actors play out their strange games upon it. But at the center of a black hole, the stage itself is being ripped apart. Space and time are curved so violently they lose all meaning. There is no calm background left. The floor beneath the quantum world has caved in. So this is the impossible situation. We have two theories. Both are triumphs. Both have been tested 1,000 times and never caught in a lie. And yet, at the center of a black hole, they collide head-on, and both of them fail at exactly the same moment. Einstein's gravity breaks because everything is too small. Quantum mechanics breaks because gravity is too strong. Each one throws up its hands and points at the other. What we need is a third rulebook, a single theory that can describe something massive and microscopic at once, where gravity and the quantum world are equally in charge. Physicists have a name for this missing theory, even though no one has ever written it down. They call it quantum gravity. It is the holy grail of modern physics, the deepest hole in our understanding of reality. And the black hole is the one place in the universe that demands it. For decades, physicists assumed this mystery would stay buried forever, locked away at the center of a black hole where no experiment could ever reach. Then one young physicist asked a question no one else had thought to ask. Not about the center, but about the edge. Because you don't have to fall all the way to the singularity to feel the strangeness. There's a boundary around every black hole, an invisible line in empty space. Cross it and there is no return. Not for a spaceship, not for light. We call it the event horizon, and it is not a wall or a surface you could touch. It's simply the point where gravity becomes so extreme that escape becomes impossible, no matter how fast you flee. Inside that line, every possible path, every direction you could ever run, leads deeper in. Not because something is chasing you, but because outward has stopped existing. Space itself is falling inward faster than light can climb out. For a long time, we thought of that horizon as nothing more than a point of no return, a one-way door, a place where the outside universe simply loses track of whatever fell through. But the event horizon is more mysterious than that. It's where the two worlds meet. On one side, the calm, ordinary space of Einstein's universe. On the other, the violent quantum abyss. The horizon is the razor-thin border between them, a boundary drawn not just by gravity, but by the quantum rules waiting just beyond it. And that thin, invisible line is about to become the most important place in this entire story. Because for decades, physicists believed the event horizon was silent, that whatever crossed it was locked away forever, sealed behind a door that only ever swings one way. A black hole, they thought, was a perfect prison, eternal, unchanging, the ultimate dead end of the cosmos. Then, in 1974, that same young physicist in a wheelchair did the math on what happens right at that boundary, where the quantum world brushes up against the edge of a black hole. And what he found didn't just surprise the world. The impossible object that swallowed everything had just been predicted to slowly disappear. And with it would vanish something even more precious than matter. It threatened to erase information itself. He wasn't trying to change the world. He was trying to prove someone wrong. In the early 1970s, Stephen Hawking was a young physicist with a fierce reputation and a body already beginning to fail him. And he was irritated. A little-known researcher named Jacob Bekenstein had made a claim that struck Hawking as absurd, that black holes might not be perfectly cold and dead. that they might, somehow, carry heat. To Hawking, this was nonsense. A black hole devours everything and gives back nothing. How could a thing that emits nothing possibly have a temperature? So he set out to crush the idea. He aimed the full machinery of quantum mechanics at the edge of a black hole, expecting to bury Bekenstein's claim for good. Instead, the math betrayed him. Because when Hawking looked closely at the event horizon, that impossibly thin line between our universe and whatever lies beyond, he found it wasn't silent at all. It was glowing. To understand what he discovered, we have to look at empty space more carefully than we ever have. We picture a vacuum as pure nothing, a perfect void. But at the quantum scale, nothing is never truly still. Even in the emptiest space imaginable, tiny pairs of particles are constantly flickering into being. A particle and its exact opposite, born together out of nothing at all. They exist for the briefest possible instant, then rush back together, collide, and vanish, repaying the energy they borrowed. It's happening everywhere, in every direction, in the space around you at this very moment. We never see it because the two always cancel out before they can be caught. Always, except at the edge of a black hole. Picture one of these pairs blinking into existence right on the event horizon. Two particles born on a knife's edge. But now they're in the most violent place in the universe, and they're ripped apart before they can find each other again. One is pulled inward, across the boundary, falling forever toward the center. The other, the survivor, is flung outward into open space. And now it has a problem. Its partner is gone. There's nothing left to cancel it out. So instead of vanishing, it lives. It escapes. A real particle streaming away from the black hole, carrying real energy out into the cosmos. To a distant astronomer, it would look as though the black hole were faintly, impossibly shining. But that energy had to come from somewhere. The universe never gives something for nothing. The particle that fell inward carried a debt across the horizon, and that debt is paid by the black hole itself. Every particle that escapes steals away a sliver of the black hole's mass. One flicker at a time, the black hole is buying its own light with its own body. This is Hawking radiation. The real calculation behind it is far deeper and stranger than any picture in words can capture. But this is the essence of it, and it rewrote everything we thought we knew. Because a black hole that radiates has a temperature. It's warm. And when Hawking worked out that warmth, he uncovered a rule that runs completely backward to everything our instincts tell us. The bigger the black hole, the colder it is. The smaller the black hole, the hotter it burns. This is the opposite of almost everything in ordinary life. A bonfire is hotter than a candle. A mountain of coals holds more heat than a single ember. But black holes obey the reverse. The giants, the monsters millions of times the mass of the sun, lurking at the hearts of galaxies, are staggeringly cold. So cold, their glow is very nearly nothing at all. In fact, a real black hole sitting out there in space today is colder than the faint afterglow of the Big Bang that fills the entire universe. And that means, for now, it's actually absorbing more warmth than it gives off. Its slow death hasn't truly begun. But that's only because the universe is still young and still warm. One day, in the deep cold of the far future, that will change. And here is where it becomes strange and beautiful. As a black hole radiates, it loses mass. But losing mass makes it smaller. And smaller makes it hotter. And hotter makes it radiate faster, which makes it lose mass even quicker, which makes it hotter still. It's a runaway, a slow unraveling that feeds on itself, quickening as it goes. For nearly all of its existence, the black hole barely seems to change, leaking so faintly the process is almost invisible. But as it shrinks, it heats. As it heats, it burns brighter. And in its final moments, after an age of near-perfect stillness, the last of the black hole does not fade away quietly. It detonates, a final, brilliant flash, releasing in a single heartbeat what it took an eternity to lose. And then, nothing. Where a black hole once sat, there is only empty space. How long does all of this take? The numbers stop meaning anything to the human mind. A black hole born from a single dying star would take longer to evaporate than the number 10 followed by 67 zeros. In years. Our universe is only around 14 billion years old. Measured against the lifetime of a black hole, all of cosmic history so far, every star, every galaxy, every moment since the beginning is less than the first flicker of an eyelash. So no, you will never watch one disappear. Neither will your children nor theirs, for a near eternity of generations yet to come. But almost forever is not the same as forever, and that one small difference changes everything. For all of human history, we believed a black hole was permanent, unbreakable. Whatever fell inside was gone, but at least it was gone somewhere, sealed away, untouchable, yet still existing behind that door that only ever swings one way. Hawking had just proven the door doesn't stay shut. Slowly, across an unimaginable ocean of time, a black hole bleeds itself away, particle by particle, until at last it vanishes from existence completely. Now look closely at what actually escapes. The radiation pouring out doesn't rise up from deep inside the black hole. It's created at the very edge, out of the trembling of empty space, and it carries no trace of whatever fell in long ago. A star, a world, a library holding the sum of all human knowledge. Every bit of it crossed the horizon and was swallowed. And the faint glow that slowly replaces the black hole knows absolutely nothing about any of it. It comes out featureless, blank, the same no matter what went in. So when the black hole finally flickers out of existence, everything it ever devoured vanishes along with it. Not hidden, not locked away in some distant vault. Erased, wiped from reality, as though it had never been there at all. And that is impossible, because there is a law, older than black holes, deeper than gravity, stitched into the very foundation of reality, that insists the universe can lose almost anything, bend almost any rule, break almost any expectation. But the one thing it can never, ever do is forget. Here is a rule so fundamental that most people have never even heard of it, because it's so deeply woven into reality that physicists rarely stop to say it out loud. The universe never forgets. It's easy to think it does. Burn a book to ash and the story seems lost forever. Shred a photograph, scatter the pieces on the wind, and the image appears gone. But look closer, much, much closer, and something quietly astonishing turns out to be true. Nothing is ever truly erased. When you burn that book, the story isn't destroyed. It's scrambled. The letters become smoke, heat, and drifting ash, But every particle of that smoke, every flicker of that heat, is still carrying a trace of what came before. In principle, if you could track every single particle with perfect precision and run the laws of physics in reverse, the smoke would gather itself back into pages. The ash would climb back into words. The book would rebuild itself, letter by letter, from the wreckage. We could never actually do this. The bookkeeping is impossibly vast. But possible in practice and possible in principle are two very different things. The point is that the information was never gone. It was hidden, jumbled beyond recognition, but it was always still there, encoded in the fine print of reality, waiting to be read. This is one of the deepest laws in all of physics. The past is never truly deleted. It's always recorded, right down to the smallest particle, in a form that could, with perfect knowledge, be rewound and replayed. The universe keeps a perfect memory of everything that has ever happened. Physicists have a name for this. They call it unitarity. And it isn't a minor technicality. It's part of the bedrock quantum mechanics is built on. It's the reason the present flows from the past in an unbroken chain. It's the reason cause leads to effect. It's the reason the universe makes sense at all. Take unitarity away, and physics doesn't just wobble, it collapses. If information can simply vanish, then the connection between what was and what will be is severed. The past no longer determines the future. Prediction becomes meaningless. The entire logical structure of reality begins to unravel. For over a century, this law had never once been broken. Not by fire, not by explosions, not by the death of stars. You can scramble information into unrecognizable chaos, but you can never truly destroy it. And then came Hawking's black hole. Look again at what he had discovered, and you'll feel the ground shift. A star falls in, trillions upon trillions of particles, each one carrying its story, its history, its information. It vanishes past the horizon. Then, across an eternity, the black hole slowly radiates that mass back out into space. But the radiation that escapes is blank, featureless. It carries no memory of the star at all. And when the black hole finally evaporates to nothing, the horizon vanishes. The interior is gone, and the information that fell inside has nowhere left to hide. It isn't scrambled. It isn't hidden in the smoke. It's gone. This is the black hole information paradox. And it is not a puzzle about black holes. It's a direct collision between our two rulebooks, exactly where we feared it would come. Einstein's gravity says the star and its information are crushed away and lost. Quantum mechanics says that is flatly impossible. Information cannot be destroyed, ever, under any circumstances. Both cannot be right. And this time, there is no center of a black hole to hide the contradiction in. The paradox plays out in plain view, in the radiation streaming across open space, where the rules of physics are supposed to work perfectly. So one of our two greatest theories has to be wrong. But which one? If Hawking was right and information truly dies inside a black hole, then quantum mechanics, the most precisely tested theory in the history of science, the theory that runs every computer and every phone and every laser on Earth, has a fatal flaw. If instead the information somehow survives and escapes, then Hawking's own calculation must be broken, and we don't understand black holes nearly as well as we thought. There was no easy way out, and so the physics world split in two. For years, the argument simmered, and it eventually crystallized into one of the most famous wagers in the history of science. In 1997, at a conference in California, two of the most brilliant minds in physics made a bet. On one side stood Stephen Hawking himself, joined by fellow theorist Kip Thorne, both convinced that black holes destroyed information for good, that here, at last, was the place where quantum mechanics finally failed. On the other side stood John Preskill, a respected physicist who refused to believe it.
Preskill was certain that quantum mechanics would hold, that information had to escape somehow, even if no one yet knew how. They wrote it down. They signed it. They agreed on a prize for the winner, an encyclopedia from which, fittingly, information can always be freely retrieved. It sounds almost playful, a friendly bet between old colleagues. But underneath the humor was one of the highest stakes disagreements in modern science. These weren't cranks arguing on the internet. These were three of the greatest physicists alive, staking their names on a contradiction that neither side could resolve. And the prize wasn't really the encyclopedia. The prize was the answer to a question that struck at the very foundation of what is real. When the universe seems to erase something forever, is it lying to us? The disagreement was profound. The stakes could not have been higher. And the honest truth is that at the moment the bet was signed, nobody on Earth knew the answer. Hawking, the man who had started it all, was so confident that information was lost that he would defend that position for years to come. His calculation was solid. His logic was airtight. Everything about the physics said the information was gone. And yet a quiet unease spread through the rest of the field. Because if he was right, the cost was almost too much to bear. It meant surrendering the one law that keeps the universe coherent. It meant accepting that reality could simply forget. Most physicists couldn't accept it. Somewhere, they felt, the information had to survive. It had to be encoded in that outgoing radiation, written in a code so subtle and so scrambled that Hawking's calculation had simply missed it. But that was little more than a hope, a conviction that the universe must make sense, with no proof to stand on. Every attempt to explain how the information could possibly escape ran into the same brutal wall. The inside of a black hole and the outside are separated by the event horizon, the one boundary in the universe that cannot be crossed from within. How can a message escape a prison that lets nothing out? How can what fell in ever reach across that one-way door to shape the light escaping into space? For a while, it looked completely hopeless. To even begin to answer it, physicists would have to do something drastic. They would have to stop thinking about space the way they always had, as an empty stage, a container, a volume things simply move through. They were about to discover that reality might be nothing like that. That everything you see, every star, every galaxy, the whole vast three-dimensional universe stretching out around you might be woven from information stored somewhere far stranger. And the first, unmistakable clue was hiding in the one place no one thought to look. On the surface of a black hole.
The clue had been sitting in plain sight for years. It was hidden inside the very thing Hawking set out to disprove, the strange idea that started this whole story. Remember Jacob Bekenstein, the young researcher whose claims so annoyed Hawking that he tried to demolish it? Bekenstein had insisted that a black hole must carry heat. But that was only half of what he said. The other half was even stranger, and at the time, almost no one took it seriously. Bekenstein claimed that a black hole has entropy. To see why that word cracked open the universe, we need to understand what entropy actually is. Most people have heard it described as disorder, a measure of mess. But underneath, it's something far more precise and far more interesting. Entropy is a measure of hidden information. Think of it this way. Imagine a room full of air. From across the room, it looks utterly simple. Just still, even air, the same everywhere. But zoom in, and that simple air is a storm of trillions upon trillions of molecules, each one racing in its own direction at its own speed. The entropy of that air counts all the hidden detail, all the information about where every molecule is and how it's moving that you can't see from the outside. More possible arrangements hidden inside means more entropy. So entropy, at its heart, is a count. It's a tally of all the microscopic information a thing is secretly holding beneath its simple surface. Now here's the collision. A black hole was supposed to be the simplest object in the entire universe. Physicists had a saying for it: a black hole has no hair. Meaning it has almost no features at all. Whatever falls in, a star, a planet, a cloud of gas, a person, the result is always the same. From the outside, a black hole can be described by just 3 numbers: its mass, its spin, and its charge. Nothing else. All the rich, intricate detail of whatever fell in appears to be completely erased. An object that simple should have almost no entropy, almost no hidden information at all. But Bekenstein, and then Hawking, working out the exact numbers, found the opposite. Black holes don't have a little entropy, they have staggering entropy. More than anything else of comparable size in the cosmos. A black hole is the single most information-dense object in the universe. And that makes no sense, until you look at where that information is written. Because here is the revelation that changed everything. When Hawking calculated the entropy of a black hole, the full measure of all the hidden information it contains, it didn't depend on the volume inside. It didn't scale with how much space the black hole encloses. It scaled with the surface area of the event horizon. Sit with that, because it's one of the strangest facts in all of physics. Everywhere else in the universe, how much you can store depends on volume. The information you could pack into a room depends on the space inside the room, its width times its height times its depth. Double every dimension of a warehouse and its capacity grows 8-fold because it's the volume that holds the contents. But not a black hole. A black hole's entire information content is set by the area of its boundary, the 2-dimensional surface wrapping around it, as though everything it ever swallowed were written not in the space within, but on the sphere enclosing it. Make that surface bigger, and it can hold more. As if the inside doesn't store information at all. As if only the surface does. It's as though you opened a vast library, walked through its towering halls expecting shelves stretching in every direction, and found that every book, every page,
Every word was somehow inscribed on the outer walls alone. The interior holds nothing. The surface holds it all. This was the first crack in one of our oldest assumptions. We had always believed information lives in volume, spread throughout the three-dimensional space inside things. The black hole was whispering something impossible, that the true information wasn't inside at all. It was painted on the boundary, and a small number of physicists dared to ask a question so audacious it sounds like madness. What if this isn't only true for black holes? What if it's true for everything? This is the holographic principle, and it is one of the most radical ideas ever to come out of serious physics. It proposes that the three-dimensional reality we live in, with its depth, its distance, its solid volume, could be encoded on a distant two-dimensional surface. That the universe of space we move through might work like a hologram. You've seen a hologram, the shimmering three-dimensional image on a banknote or a credit card. It looks like it has real depth, real dimension. But it's an illusion, projected from a flat, two-dimensional pattern etched on the surface. All the information needed to build that 3D image is stored on a 2D sheet. The holographic principle suggests reality itself might work the same way. That the depth and volume of the world around you could be a kind of projection, the readout of information written on a faraway surface. That the inside of the universe might be woven from a code stored on its edge. For years, this was a beautiful, unprovable dream. A wild suggestion with nothing solid beneath it. Then, in 1997, a physicist named Juan Maldacena wrote down the mathematics that made it real. He discovered something breathtaking. Two completely different descriptions of the same universe that turned out to be secretly, perfectly identical. On one side, a three-dimensional space with gravity working inside it, black holes and all. On the other, a purely quantum description living on the boundary of that space with no gravity at all, just particles and their interactions. They looked like utterly different worlds. But Maldacena showed they were two languages telling the exact same story. Anything happening in the three-dimensional interior, gravity included, was perfectly mirrored by something happening on the two-dimensional surface. The bulk and the boundary were the same reality, written two ways. This was a mathematical bridge between a volume and its surface, a rigorous, working example of a universe that is truly a hologram. It has become one of the most influential and heavily tested ideas in all of modern physics, cited in tens of thousands of papers. For the first time, holography wasn't just a dream, it was a tool. And it changed the entire information paradox. Because if a black hole and everything around it can be perfectly described by quantum physics living on a distant surface, physics with no black hole, no singularity, no one-way door, then that description must obey the ordinary rules. It must preserve information. Nothing can be lost. So the information can't be dying inside the black hole. Somewhere in that flawless mirror on the boundary, the star that fell in must still be there. Its story intact, its memory preserved, encoded in a language we were only beginning to learn to read. For the first time, physicists had a real reason, not just a hope, to believe the information survives. But a reason is not a mechanism. Knowing the information must escape is not the same as knowing how. The boundary swore that nothing was lost, yet inside, at the black hole itself, the escape route was still nowhere to be found. And when physicists went back to that horizon, armed with all these new ideas, to finally work out exactly how a particle falling in could still leave its mark on the light escaping out. They didn't find an answer. They found something far worse. They found fire. For 30 years, the information paradox had been a war of ideas, a clash of equations and instincts about a place no one could see. It was strange. It was maddening, but it stayed politely abstract. In 2012, 4 physicists turned it into a nightmare. Their names were Almheri, Marolf, Polchinski, and Sully, and physics remembers them by their initials, AMPS. They weren't trying to break anything. They were trying to do the opposite. They set out to take the best, most reasonable ideas the field had assembled, Hawking's radiation, the survival of information, the lessons of holography, and simply check that they all fit together. They didn't fit. They collided so violently that the wreckage pointed to something monstrous waiting at the edge of every black hole. To feel the force of what they found, we have to return to that thin, glowing boundary, the event horizon, and look at what physics now demanded of it. By 2012, the best thinking said 2 things had to be true at once. The first came from holography and the outgoing radiation. If information truly escapes a black hole, it can't come out blank. It has to be smuggled out, written into that Hawking radiation in a hidden code. And the way nature carries a secret in the quantum world is through a delicate connection called entanglement, a deep link that ties 2 particles together so that one carries information about the other. For the black hole to release its memory, each new particle escaping at the horizon had to be entangled with the whole swarm of radiation that had already escaped before it. That was the lifeline. That was how the message got out. The second thing came from Einstein. General relativity makes one calm, confident promise about the event horizon: that there is nothing there. Nothing special, nothing violent. The horizon isn't a wall. To anyone falling in, crossing it should feel like nothing at all, just empty space slipping by. Einstein called this the equivalence principle, and it is one of the most tested ideas in all of science. A falling astronaut sails across the horizon and, for a while, doesn't even notice they've passed the point of no return. Empty space, right up until the end. But for that space to be empty and peaceful, each particle born at the horizon must be entangled with its own infalling partner, the twin it was created with, plunging inward. That gentle pairing is exactly what makes the horizon smooth. Break it, and space itself is no longer empty there. Now, watch the trap close. The escaping particle is asked to be fully entangled with 2 different things at once. To carry information out, it must be bound to all the old radiation that fled before it. To keep the horizon peaceful, it must be bound to its infalling partner. And the quantum world forbids this. There is an ironclad rule, as strict as anything in physics, that says a connection this complete cannot be shared. If a particle is fully entangled with one thing, it cannot also be fully entangled with another. The lifeline and the smooth horizon demand the very same bond. They cannot both have it. Something has to break. And AMPS followed the logic to its brutal conclusion. If information really does escape, if quantum mechanics wins and the message gets out, then the particle must stay bound to the old radiation. Which means the other bond, the gentle one that kept the horizon empty, has to be severed. And when you snap that bond, the horizon does not stay quiet. It erupts. Breaking that entanglement releases a torrent of energy right at the boundary, right where empty space was supposed to be. Not a smooth crossing, not gentle nothingness. A seething wall of blistering high-energy particles, hotter than anything imaginable, blazing at the edge of the black hole. They called it a firewall. And it meant that an astronaut falling in wouldn't drift peacefully across an invisible line. They would slam into a wall of fire and be incinerated in an instant, annihilated the moment they reached the horizon. This was a catastrophe, and not because firewalls are frightening. It was a catastrophe because it meant Einstein was wrong. A firewall shreds the equivalence principle, the untouchable promise that falling across a horizon should feel like nothing. It says the horizon is not empty space, but the most lethal surface in the universe. To save quantum mechanics and let information escape, AMPS had been forced to set fire to general relativity. And so physicists were cornered into an impossible choice, with no comfortable way out. Either information is destroyed, and quantum mechanics fails, and the universe can forget. Or a firewall rages at the horizon, and general relativity fails, and Einstein's smooth spacetime is a lie. Every path led off a cliff. Give up quantum mechanics, or give up relativity, or accept a wall of fire where the greatest theory of gravity swears there is nothing at all. There was no gentle answer left standing. The field descended into open war. Because now, the old escape routes weren't just unproven, they were under siege. Every proposed solution had to survive the firewall, and each one demanded a different sacrifice. Some physicists rallied behind an idea called complementarity, the notion that maybe there's no contradiction at all because no single observer ever sees both sides of the paradox. The astronaut who falls in and the scientist who stays outside would witness completely different, irreconcilable versions of events. And, the argument went, since they can never compare notes, the universe is allowed to tell each of them a different story without ever being caught in a lie. It was clever. To some, it felt like a dodge. Others took a more radical swing and denied the premise entirely. What if a black hole has no smooth, empty interior to fall through in the first place? This is the fuzzball idea. The proposal that a black hole isn't a void wrapped around a singularity at all, but a dense, tangled ball of structure packed right up to where the horizon should be. There's no serene inside to protect because there's no true inside at all. What looks from far away like an empty black sphere is, up close, solid all the way through. Every scrap of information stored right there in the structure, never lost, never hidden behind a horizon. And then came the strangest idea of them all, one that would quietly reshape the entire search. What if the escaping radiation and the inside of the black hole aren't separated by an impossible barrier because they're secretly connected by something we never thought to include? What if they're joined by a wormhole? It sounds like pure fantasy, but it grew from a haunting coincidence two physicists had noticed. That entanglement, the invisible quantum thread linking distant particles, behaves suspiciously like a tunnel through space connecting them. Two ideas that seemed to have nothing to do with each other, quantum entanglement and wormholes in spacetime, might, in fact, be the very same thing wearing two disguises. A quantum link between particles and a bridge through the fabric of space could be one phenomenon seen from two directions. If that were true, then the information trapped inside a black hole wouldn't need to smash through the horizon to escape. It could already be linked to the outside, threaded through hidden tunnels sewn into space-time by entanglement itself. The prison would have secret passages built into its very walls. It was a beautiful, almost reckless suggestion that entanglement itself might be the thread stitching space together. And for a while, it was little more than a whispered possibility, a slogan without a full theory behind it. But it planted a seed, a hint that space, entanglement, and information were tangled together far more intimately than anyone had dared to imagine. For years, the war ground on with no victor. Firewalls, fuzzballs, wormholes, and observers who see different worlds. Brilliant ideas, all of them, and none able to win. The paradox that had begun with a single particle at the edge of a black hole had grown into a full-blown crisis at the foundations of physics, and there seemed to be no way through. And then, between 2019 and 2020, someone finally did the calculation. Not a slogan, not a hope, a hard, rigorous calculation built from gravity itself, one that traced exactly what happens to the information as a black hole evaporates. And when the numbers came back, they revealed something no one had been able to prove in nearly 50 years. The information comes out. To understand the breakthrough, you have to know exactly what a victory would look like. And for that, we have to meet a curve. Back in 1993, years before the Firewall, before Maldasena's holographic bridge, a physicist named Don Page asked a beautifully simple question. Forget how information might escape a black hole. Just assume that it does, that quantum mechanics is right, and nothing is ever lost. If that's true, then what should the radiation actually look like as the black hole slowly evaporates? Page worked out the answer, and it took the shape of a curve, a specific rise and fall that the information in the radiation would have to trace over the black hole's lifetime. Today, we call it the Page curve, and it became the fingerprint of a universe that never forgets. Here's what it says. Picture measuring the information carried by the radiation as it streams away, from the black hole's birth all the way to its final flash. In the beginning, as the black hole starts to glow, the radiation looks utterly random, blank and featureless, exactly as Hawking said. Each escaping particle seems to carry no memory of what fell in. And for the first half of the black hole's life, this only deepens. The radiation appears more and more scrambled, more disordered, spilling out into space like meaningless static. If you were tracking the hidden information, the line would climb and climb, the black hole seemingly locking its secrets further and further away. If Hawking were right, if information truly dies, that line would simply keep climbing until the black hole vanished, secrets lost forever. But the Page curve does something else. It rises, and then, at the halfway point, it turns. That turning point, the Page time, is the moment everything changes. Past it, the line begins to fall. The radiation, which had looked like pure randomness, quietly starts to carry information back out. Particle by particle, the secrets begin to leak into the escaping light, until by the time the black hole delivers its final flash, the line has fallen all the way back down. Every scrap of information the black hole ever swallowed has returned to the outside universe, written in the subtle correlations of the radiation. That downward turn is the whole ball game. A curve that rises and then falls means information is conserved. The universe keeps its memory. A curve that only rises means information is destroyed. Hawking's nightmare, the death of quantum mechanics. So for decades, the challenge crystallized into one razor-sharp goal. Forget the words and the philosophy. If you could start from the physics of gravity itself and derive that downward bend, if you could make the page curve fall out of the equations, you would prove the information escapes. And for nearly 50 years, no one could do it. Every time physicists ran Hawking's calculation, they got Hawking's answer, the line that only climbs. The radiation came out blank, the information stayed lost, the curve never turned. The mathematics of gravity itself seemed to insist that information dies. To get the turn, it looked like you'd need a complete theory of quantum gravity, the very thing we don't have. The page curve stood there like a locked door, and no one held the key. Then, in 2019 and 2020, several groups of physicists, working along parallel paths, finally forced the door open. And the way they did it was so unexpected that it startled even them. They had been using the wrong instructions for how to calculate with gravity. To find the radiation coming out of a black hole, physicists use one of the strangest and most powerful tools in all of physics, the gravitational path integral. The idea, which traces back to Richard Feynman, is that to work out what a system does, you don't follow a single history. You add up every possible history at once, every path reality could take from start to finish, all blended together into one grand sum. It sounds insane, but it is one of the most successful methods ever devised. For 50 years, when physicists applied this tool to a black hole, they quietly made an assumption. They summed up the ordinary histories, the straightforward shapes of space-time, and left it there. And that gave the failing answer, the curve that only rises. The breakthrough was the discovery that they had been leaving something out. There were extra shapes of space-time that also belonged in the sum. Strange, counterintuitive geometries that connect the black hole's interior to the distant radiation through hidden tunnels, bridges threaded through the calculation itself. Because the path integral demands every possibility, these exotic geometries had every right to be there. Physicists had simply never thought to include them. These new contributions carried a name that captures how bizarre they are. The pieces of the black hole's interior that turn out to secretly belong to the outside radiation were called islands, regions deep inside the black hole that, against all intuition, count as part of the world outside it. And the strange geometries linking them across the calculation were replica wormholes, tunnels stitching different copies of the black hole together inside the sum over histories. You don't need to follow the machinery. Here is what matters. When physicists finally added these missing pieces, the islands, the replica wormholes, into the gravitational path integral and turned the crank, the page curve appeared. The line rose, and then, exactly on schedule, at exactly the page time, it turned. It bent downward and fell all the way back to the ground, precisely as a universe that conserves information demands. Out of the raw mathematics of gravity, with no new physics bolted on, no quantum gravity theory of everything required, the downward bend fell out on its own. After nearly 50 years,
information had been shown to escape a black hole. Not hoped, not argued, calculated, from gravity itself. And notice what quietly happened along the way. Remember that reckless idea from the Firewall Wars, that entanglement might secretly be wormholes, that the inside and outside of a black hole could be linked by hidden tunnels through space-time. The islands and replica wormholes were that idea made rigorous. The interior really does reach out and touch the escaping radiation through connections woven into the fabric of the calculation. The wild slogan had become hard mathematics.
The prison always had secret passages, and now the equations revealed exactly where they were. This was, without exaggeration, one of the most important results in theoretical physics in a generation. A puzzle that had defeated the greatest minds for half a century, Hawking's own paradox, had finally, decisively begun to yield. The universe, it seems, does not forget after all. Even a black hole, the ultimate devourer, eventually gives up everything it swallowed, its secrets encoded in the faint glow of its own slow death. But, and this matters because honest science demands it, the story is not fully closed. What physicists have shown is that the information comes out. The page curve is real, and it emerges from gravity as it should. But the deeper question of exactly how, the precise, physical, moment-by-moment mechanism by which a specific memory of a specific thing is threaded into specific escaping particles, is still not completely understood. The island's calculation tells us the books are being returned. It doesn't yet let us stand at the horizon and read them as they leave. And much of this work lives in simplified, idealized model universes, easier to calculate in than our own. Carrying it fully into the real cosmos is work still underway. So the paradox is not so much solved as it is broken open, cracked at last after 50 years, with light finally pouring through, even if we cannot yet see all the way to the bottom. Which leaves one final question. All of this, the radiation, the paradox, the firewall, the islands, has been a story told in equations and imagination. A war fought entirely with mathematics about an object we have never touched. So, is there any way to actually test it? Can we ever reach out and check whether the universe truly works this way? Or are black holes destined to remain forever beyond our grasp, their deepest secrets locked behind an horizon we can never cross? As it turns out, we've already begun to try. For most of this story, the black hole has been a creature of the imagination, a place we could only visit through equations. For a century, no human being had ever seen one. We believed in them the way we believe in things glimpsed only through mathematics, confidently, but at a distance. Then, in 2019, we took its picture. An effort called the Event Horizon Telescope did something that sounds impossible. A single telescope large enough to see a black hole would have to be the size of the Earth itself. So astronomers built exactly that, by linking radio dishes scattered across the entire planet, from Hawaii to Spain to the South Pole, and fusing them into one virtual telescope as wide as the world. They aimed it at a supermassive black hole in a galaxy 55 million light-years away, and after processing a mountain of data, an image emerged. A ring of blazing light,
curved around a circle of perfect darkness. That dark center is the shadow of the event horizon, the silhouette of the point of no return, traced out by the glow of superheated matter swirling around it. For the first time in history, we were looking directly at the edge of a black hole. A few years later, they did it again, capturing the monster at the heart of our own galaxy. The impossible object was real, exactly where Einstein's equations had placed it, shaped exactly as they predicted. But a photograph, breathtaking as it is, only shows us the outside. It confirms the black hole exists. It cannot tell us whether information escapes or whether the horizon hides a firewall. For that, we needed new senses. And in 2015, we grew one. For the first time, we heard a black hole. An observatory called LIGO detected gravitational waves, ripples in the fabric of space-time itself, set off when two black holes spiraled together and merged over 1 billion years ago. As they collided, they sent a tremor rolling out across the universe, stretching and squeezing space by less than the width of a proton by the time it washed over Earth. And we felt it. This gave us something a picture never could. Gravitational waves let us listen to the horizon ringing like a struck bell in the moments after two black holes become one. And buried in that ringing is a test. If the horizon is the smooth, empty boundary Einstein promised, it rings one way. But if something is different there, a firewall, a fuzzball's hard surface, some quantum structure where empty space should be, the ringing might carry a faint echo, a subtle aftershock arriving just behind the main signal. Physicists are combing through the data for exactly these echoes right now. So far, the signals look as Einstein predicted, but the precision is still growing, and the search is far from over. Yet even this only probes the outside. The radiation itself, Hawking's faint glow, the very thing carrying the information out, is still hopelessly beyond reach. A real black hole is so cold that its whisper of radiation is drowned out completely by the warmth of the universe around it. We will almost certainly never catch it streaming from a black hole in the sky. So physicists did something audacious. If we cannot bring the experiment to the black hole, we build a black hole in the lab. You cannot trap gravity on a table, but you can trap its echo. The key insight is that a black hole is really about one thing, a point of no return, a place where escape becomes impossible. And you can recreate that condition without any gravity at all. Imagine a river flowing toward a waterfall, faster and faster. A fish trying to swim upstream can make headway until the water flows faster than the fish can swim. Past that line, no matter how hard it struggles, it's swept over the edge. That line is a point of no return, built entirely out of flowing water. Physicists build the same thing with sound. They create a fluid, sometimes an ultra-cold quantum state of matter near absolute zero, and make it flow faster than the speed of sound within it. Now, sound waves become the trapped swimmers. Once they cross the line where the fluid outruns them, they can never travel back upstream. They've reached a point of no return for sound, an artificial horizon, a black hole for waves instead of light. And here is the astonishing part. When physicists examined these laboratory horizons, they found them glowing, with a faint hiss of sound waves creeping out of the trapped region, born right at the artificial edge. The very thing Hawking predicted for real black holes was appearing in a tank on a laboratory bench.
Careful experiments have now measured this analog radiation and found that it even carries the temperature relationship Hawking's math demands. We cannot yet touch a real black hole's glow, but we may have watched its echo, created and captured by human hands. Physicists have gone further still, reaching for the strangest frontier of all. If the deepest lesson of the paradox is that a black hole is really a scrambler and re-emitter of quantum information, then perhaps the place to study it is a machine built to manipulate quantum information directly, a quantum computer. In 2022, a team programmed a quantum processor to model a simplified system that behaves, mathematically, like two mouths of a wormhole and watched a signal pass across it. Headlines roared that scientists had made a wormhole in the lab. They had not. Nothing tore open in space-time. No bridge through the universe appeared. What they had built was a small quantum system sharing the same underlying mathematics as a toy wormhole. A simulation of the idea, not the thing itself. It was a genuine milestone, but a modest one, and it was badly oversold. Still, it hints at a remarkable future, using quantum computers as laboratories to test the very ideas that have haunted black hole physics for half a century, running experiments on the mathematics of space-time that no telescope could ever perform. None of this is the final proof. We have not read the information leaving a black hole. We have not confirmed the islands, or ruled out the firewall, or held quantum gravity in our hands. The deepest questions are still open, still waiting. But look at how far the ground has shifted. A problem that began as pure thought, a young man doing math on the edge of a black hole, has grown into a science with pictures, with sounds, with experiments on laboratory benches and inside quantum machines. The untestable is slowly, stubbornly becoming testable. And that changes what these questions are. They are no longer just philosophy. They are becoming a frontier. We are learning, at last, how to cross. We began with a single, simple question. A star dies, a black hole forms, something falls in, and when the black hole finally fades away, where did everything go? It seemed at first like a question about black holes. It was really a question about whether the universe makes sense. Follow that one thread and watch what it unravels. It began with a young Stephen Hawking trying to prove a rival wrong, only to discover that black holes glow and that they die. That single result set off a paradox that struck at the foundation of physics itself. A war between our two greatest theories fought over the fate of a single particle at the edge of a black hole. Chasing the answer forced us to imagine that reality is a hologram, that the world of depth and volume around us might be woven from information written on a distant surface. It drove us into the fire of the firewall and out the other side through hidden tunnels in space-time, until at last a calculation drawn from gravity itself revealed the answer Hawking had doubted. The information comes back. The universe does not forget. And notice what this journey really was. Every step, Hawking's radiation, the paradox, holography, the firewall, the islands, was an attempt to force our two rulebooks into the same room and make them speak. The reason black holes matter so much is that they are the one place in all of creation where the very large and the very small are crushed together, where gravity and the quantum world cannot look away from each other. Every discovery in this story has been a fragment of the theory we still don't have, quantum gravity, glimpsed in the light of a black hole's slow death.
That is why we keep returning to these objects. Not because they are dark or violent or strange, though they are all of those things. We return because a black hole is the one place where the deepest laws of reality are laid bare and forced to reconcile. It is nature's ultimate laboratory, holding the answer to the greatest unfinished question in physics: how gravity and the quantum world, space and time finally fit together into a single, unbroken truth. We have not reached that truth yet. The paradox is cracked open, not closed. The firewall still smoulders in the background. Quantum gravity remains the great mountain we have only begun to climb. There are answers out there, still hidden behind the horizon, waiting for minds not yet born. But we have learned something profound in the trying, that an object which seems to be the ultimate ending, the place where stars die and light itself is swallowed, may be exactly the opposite. It may be a beginning, a doorway, because a black hole is not simply where things fall in and vanish. It may be the one place in the universe patient enough to hold its greatest secret. And, at the very end, generous enough to give it back.